There is a planet sitting at the outermost boundary of our solar system that by every reasonable physical principle should be the most serene and undisturbed world in existence. It orbits roughly 4.5 billion kilometers from the Sun. Less than 1/10 of a single percent of the sunlight that warms our planet ever reaches its cloud tops. Its atmosphere hovers around -214 degrees Celsius. Every number points in the same direction: stillness. A frozen blue sphere drifting in near total darkness, where almost nothing happens because almost nothing drives it to. It does not work that way. Neptune's winds regularly exceed 1,200 kilometers per hour, faster than any sustained wind ever recorded on any other planet in the solar system. It generates storm systems large enough to contain the entire Earth, sustains them for years, then makes them disappear completely, only to grow new ones from scratch somewhere else entirely. It radiates into space more than double the heat it ever receives from the Sun. The farthest major planet from our star, the coldest of the 4 giant worlds, turns out to be, by a wide margin, the most atmospherically violent world we have ever measured. Let us start with something so familiar it barely registers as a rule. The closer you stand to a source of heat, the warmer you feel. Move away, and that warmth diminishes with distance until it fades into nothing useful. This describes, at its most fundamental level, how energy spreads through space. Heat radiates outward in all directions simultaneously, and because it covers an ever-expanding sphere as it travels, the energy density at any given point drops as the square of the distance from the source. Double the distance and the energy hitting a given area falls to 1/4. Triple it, and you are down to 1/9. The Sun converts roughly 4 million tons of its own mass into pure radiated energy every single second, with a core temperature near 15 million degrees. That output is the engine behind nearly every process that moves or transforms matter on any world orbiting it. Mercury, the innermost planet, receives approximately 7 times the solar energy per square meter that Earth does, with a sunlit face above 400 degrees Celsius. Venus, despite sitting farther out, traps incoming heat so effectively beneath its thick carbon dioxide atmosphere that its surface climbs above 460 degrees. The hottest planet in the system despite not being the closest. Earth orbits at exactly the right distance to keep liquid water stable, weather systems running, and life possible. Mars, about 1.5 times farther from the Sun, receives less than half Earth's solar energy and averages 60 degrees below zero. Cross the asteroid belt and continue to Jupiter at 5 times Earth's distance, and sunlight has thinned to about 4% of what reaches us. Saturn, at 10 times Earth's distance, receives barely 1%. Uranus, at 20 times Earth's distance, gets a fraction of a fraction. And then, orbiting nearly 30 times farther from the Sun than Earth, sits Neptune. By the time sunlight reaches Neptune's cloud tops, a journey taking over 4 hours even at the speed of light, it has diluted to roughly 900 times weaker than what falls on Earth, where our planet intercepts about 1,360 watts of solar energy per square meter. Neptune receives around 1.5 watts. A dim porch light seen from across a valley would outperform the Sun as a heat source from that distance. This is not a metaphor. It is, within an order of magnitude, literally true. That gradient, close means warm and energetic, far means cold and quiet, is the organizing principle of the entire solar system. It shapes surface temperatures, governs atmospheric chemistry, and sets the pace at which weather is allowed to operate. And it builds, with mathematical certainty, toward one conclusion. The outermost major planet should be the most atmospherically inert world in the system. Almost no energy arrives. Almost nothing should happen. For well over a century after Neptune's discovery, that was exactly what scientists expected. Neptune was not found by observation. it was found by mathematics. Astronomers tracking the orbit of Uranus in the mid-19th century noticed persistent discrepancies. The planet was not quite where Newtonian mechanics said it should be. Something unseen was pulling at it gravitationally. The French mathematician Urbain Le Verrier worked through the equations and identified a specific patch of sky where an undiscovered planet would have to sit to produce exactly those perturbations. When the German astronomer Johann Gottfried Galle pointed his telescope at that location in September 1846, he found Neptune within 1 degree of the predicted position on the very first night he looked. A world discovered entirely on paper before anyone confirmed it by eye. But finding a planet and genuinely understanding one are different problems. From Earth, Neptune appears as a disk barely 2 arcseconds wide, roughly the apparent size of a small coin viewed from 3 kilometers away. What anyone really knew for over a century was the bare outline. An orbital period of 165 years, a diameter nearly 4 times Earth's, and a deep blue color produced by methane-absorbing red light. Based purely on the logic of solar energy and distance, scientists calculated that Neptune's expected equilibrium temperature should hover around -228 degrees Celsius, cold enough to slow atmospheric chemistry to near stasis. A world this far from the sun simply had no business being active. A century of careful reasoning all pointed the same direction. Then came a rehearsal that seemed to confirm every assumption perfectly. In January 1986, Voyager 2 swept past Uranus, Neptune's closest analog in terms of size, mass, and composition. The imaging team at NASA's Jet Propulsion Laboratory expected at minimum some visible weather structure, a few cloud bands, perhaps some storm features. What came back was almost nothing. Uranus appeared as a smooth, nearly featureless blue-green sphere, so devoid of visible weather that some scientists initially suspected the camera filters were washing out contrast that was actually there. They were not. Only after aggressively processing the data did faint cloud bands and subtle polar features emerge. Features completely invisible in any less carefully enhanced version of the images. The explanation seemed to fit perfectly. Uranus sits 20 times farther from the sun than Earth, receiving only a trace of solar energy, and it radiates essentially no internal heat. Without either the sun or its own interior providing meaningful power, the atmosphere simply had nothing to work with. Stillness was the expected outcome of the energy budget, and if that logic held for Uranus, it seemed to promise something even quieter for Neptune, farther from the sun, receiving even less energy. Some scientists privately speculated that the Neptune flyby, still 3 years away, might prove to be the least visually interesting encounter of Voyager's entire 12-year mission. By 1989, Voyager 2 was a 12-year-old machine operating far beyond its original design parameters. It had launched in August 1977 to exploit a rare planetary alignment occurring only once every 175 years, a geometry allowing a single spacecraft to use each giant planet's gravity as a slingshot toward the next. Along the way, it had already rewritten major portions of planetary science, documenting volcanic eruptions on Jupiter's moon Io, mapping Saturn's extraordinary ring system, and measuring Uranus's unusual tilted magnetic field. Each encounter built on the last, a 4-planet relay race through the outer solar system with no possibility of a second pass. By the time it approached Neptune, its primary radio receiver had failed years earlier, its camera platform had jammed during the Saturn flyby and required painstaking remote reprogramming to restore, and its signals were so faint after traveling over 4 billion kilometers that engineers had to link antennas across 3 continents simultaneously just to reconstruct a single image. Every transmission took over 4 hours to reach Earth. The imaging team at JPL had spent months preparing for a flyby window lasting only hours. Neptune rotates once every 16 hours, so Voyager would only ever see one hemisphere in real detail before its momentum carried it past and out into interstellar darkness forever. Every camera angle had been calculated months in advance. There would be no second attempt. Whatever Voyager captured on August 25, 1989, would stand as humanity's only close-up record of this world for decades to come. Expectations were modest. Neptune's moon Triton and the planet's magnetic field were the primary targets. The atmosphere was treated almost as an afterthought, the part everyone assumed would simply confirm what Uranus had already shown. As Voyager 2 closed on Neptune through early August, the first images showed exactly what everyone expected: a quiet blue disk, unremarkable, tinted by methane. But as the spacecraft drew closer and resolution sharpened over the following days, details appeared that had no business being there. Bright cloud streaks, dark oval structures embedded in the blue background, long organized bands suggesting coherent wind currents rather than random turbulence. With each new image, the atmosphere revealed more structure and more motion than any prediction had allowed for. By the time the closest approach images arrived, the mood in the JPL imaging room had shifted from routine anticipation to something closer to disbelief. The first thing anyone noticed was a feature that simply should not have existed. Sitting in Neptune's southern hemisphere was a massive dark oval approximately 13,000 kilometers across at its longest axis and roughly 6,600 kilometers wide, large enough to contain the entire Earth inside its borders. Scientists named it the Great Dark Spot, a deliberate reference to Jupiter's Great Red Spot, because the resemblance was impossible to ignore. Here, on the coldest and most distant of all the giant planets, sat a storm system rivaling the most iconic weather feature in the solar system. It was not alone. A second smaller dark oval appeared farther south. Between the two, an isolated bright cloud raced around the entire planet at astonishing speed, completing a full circuit approximately every 16 hours. Someone on the imaging team gave it the nickname the Scooter, an oddly cheerful label for something fast enough to circle a whole planet in under a day. But the images, dramatic as they were not the most shocking part. It was the numbers that followed them. By tracking cloud features across successive images and measuring how far they moved relative to Neptune's known rotation rate, Voyager's instruments calculated actual atmospheric wind velocities. At the equator, winds blew backward, retrograde, directly against the planet's own direction of spin, at speeds approaching 900 kilometers per hour. At higher latitudes, the winds reversed direction and accelerated further, exceeding 1,200 kilometers per hour. That is the highest sustained wind speed ever measured on any planet in the solar system, before or since. To understand how strange that number really is, the strongest sustained winds ever recorded in a terrestrial hurricane reached approximately 215 kilometers per hour. A storm violent enough to level reinforced structures and strip bark from trees. Neptune's winds, moving through an atmosphere nearly 200 degrees below zero and fed by a sliver of sunlight 900 times weaker than what reaches Earth, blow nearly 6 times faster. A hurricane on Earth draws its energy from warm tropical ocean water heated intensely and directly by the sun. Neptune has neither a warm ocean nor meaningful sunlight. Its entire solar energy budget would not power a fraction of a single terrestrial storm, and yet its winds outpace our strongest hurricanes by a factor that should not exist under any conventional accounting of energy and weather. These were not brief gusts. The wind pattern across Neptune's disk showed a structured, organized system arranged into alternating bands at different latitudes. broadly similar to Jupiter's banded weather, but on a grander scale. Where Jupiter splits its energy across dozens of competing narrow jet streams that constantly create friction with each other, Neptune concentrates its motion into just a few enormous planet-spanning channels. Fewer, larger wind bands mean less energy wasted on internal friction and more of it converted directly into raw speed. The great dark spot itself behaved like a living structure. It rotated counterclockwise and drifted steadily westward relative to the surrounding atmosphere. Bright white clouds of frozen methane formed along its edges wherever rising gas cooled and crystallized at the vortex's boundary, a visible signature of enormous quantities of air being forced upward by the storm's rotation. Its shape even oscillated over a cycle of roughly 8 days, stretching and compressing in a rhythm suggesting constant dynamic interaction with the surrounding jet stream. On Jupiter, the Great Red Spot has held its shape for centuries. Scientists initially assumed Neptune's version would behave similarly. That assumption would prove as wrong as every other prediction Voyager had just dismantled. When the Hubble Space Telescope turned toward Neptune in 1994, only 5 years after Voyager's flyby, the expectation was straightforward. The Great Dark Spot would still be there. It was gone, not weakened or shrunken. Gone entirely, as if it had never formed. The smaller southern vortex photographed alongside it had also vanished. In their place, a new dark spot had appeared in the opposite hemisphere, in the north, where nothing had previously been detected. Nothing else in the solar system behaves like this. Jupiter's storms persist across human lifetimes. Neptune generates planetary-scale vortex systems, sustains them for a few years, destroys them completely, and grows new ones elsewhere, as if the atmosphere treats permanence as something to be avoided. Continued observation only reinforced how routine this instability really is. Astronomers now estimate that some form of major dark vortex exists on Neptune roughly half the time, being continuously generated and destroyed in a cycle suggesting a perpetual internal engine. A storm detected by Hubble in 2018 offered the clearest look yet at how these vortices die. About 7,400 kilometers across, it began drifting southward toward the equator, exactly where models predicted the powerful wind shear would tear it apart. Then, in 2020 observations, it simply reversed course and began drifting back the way it came, contradicting every prediction built from the planet's own history. A second smaller dark feature appeared nearby, apparently a fragment that had broken away before eventually fading. If that fragmentation was confirmed, it represented the first time anyone had directly witnessed a Neptunian dark spot in the actual process of breaking apart, rather than simply noticing afterward that one had disappeared. The implication is significant. If Neptune's vortices routinely fragment rather than dissolve quietly, the energy released during breakup could flow back into the surrounding atmosphere and seed conditions for the next storm. Neptune may be running a self-sustaining cycle where the wreckage of each dying system becomes raw material for whatever forms next. In 2023, a research team using the European Southern Observatory's Very Large Telescope achieved something previously considered essentially impossible: detecting one of Neptune's dark spots directly from the ground without a spacecraft or space telescope. The observation did not just produce an image, it produced a spectrum. That spectrum revealed something photographs alone had never shown. The dark appearance was not simply a gap where clouds were absent. The aerosol particles inside the vortex itself had physically darkened, meaning the storm was actively altering the chemistry of the material trapped within it. Neptune's broader cloud cover proved equally unstable. Beginning around 2019, astronomers noticed something striking. Clouds were not just thinning gradually, they were disappearing within months. By 2020, the mid-latitude cloud bands that had defined Neptune's appearance across nearly 3 decades of observation had almost completely vanished. The cause traces back to the 11-year cycle of the Sun's own ultraviolet output. When solar ultraviolet activity increased, Neptune's cloud cover followed roughly 2 years later. When solar output dropped, the clouds faded in step. Ultraviolet light breaks apart methane molecules in Neptune's upper atmosphere, producing complex hydrocarbon compounds that serve as condensation nuclei for cloud formation at lower altitudes. When ultraviolet input decreases, that supply chain slows, and the clouds never form. Even at a distance where sunlight has faded to 1.5 watts per square meter, the sun still reaches far enough to rewrite Neptune's entire visible appearance within a couple of years. The winds, however, never paused once. The jet streams kept howling at full recorded velocities throughout the entire episode, proof that the clouds were only ever the visible signature of something deeper, while the actual atmospheric engine never stopped running. None of what Voyager measured can be explained by sunlight. Neptune receives such a tiny fraction of Earth's solar energy that even if its atmosphere converted every incoming photon into wind with perfect efficiency, which physics explicitly forbids, the result would still fall far short of the measured wind speeds. The sun is simply not paying for this. Voyager's infrared instruments provided the critical missing piece. When scientists measured how much heat Neptune was radiating into space and compared it to how much solar energy it was absorbing, the result transformed the entire mystery. Neptune radiates approximately 2.5 times more energy than it receives from the sun. More than half of everything powering its atmosphere is coming not from outside the planet, but from within. The most straightforward explanation is residual formation energy. When giant planets first assemble from collapsing gas and dust, the gravitational energy released during that collapse gets partly trapped as heat deep inside the new planet. Over billions of years, that trapped heat slowly migrates toward the surface and escapes into the atmosphere. Jupiter and Saturn, being far more massive, trapped enormous reserves and continue releasing them steadily. Neptune's ratio fits within that same framework. What is genuinely perplexing sits in the comparison to Uranus. In nearly every measurable physical respect, Uranus is Neptune's twin. Similar mass, nearly identical diameter, broadly similar composition. By every obvious measure, they should share a similar internal heat budget. They do not. Uranus radiates almost no excess heat at all, sitting in near-perfect thermal balance with incoming sunlight. And the result is the smooth, featureless world Voyager photographed in 1986. Calm, not because it lacks Neptune's ingredients, but because it apparently lacks the engine. The leading explanation focuses on Uranus's extraordinary axial tilt of roughly 98 degrees, most likely the result of a catastrophic ancient collision early in the solar system's history. Some researchers believe that same impact disrupted Uranus's internal heat transport, creating a stable internal layering that traps remaining heat beneath an insulating barrier and prevents it from ever reaching the atmosphere. Neptune, having apparently avoided any comparable disaster and maintaining a more modest tilt of about 28 degrees, may simply allow its internal heat to rise freely from core to cloud tops. The honest answer is that nobody yet fully knows, and resolving it will almost certainly require a dedicated mission to both ice giants. But even a confirmed internal heat source only explains half the mystery. The total heat flux escaping Neptune's interior is modest in absolute terms, a fraction of a watt per square meter, far less than what would naively be needed to drive winds this extreme. Something about how Neptune's atmosphere handles that small energy input must be dramatically amplifying it. Three overlapping factors appear to enable that amplification. The first is the complete absence of any solid surface. When a hurricane crosses a coastline on Earth, it weakens rapidly because terrain drains kinetic energy through friction. Neptune has no equivalent obstacle anywhere near its visible atmosphere. Its envelope thickens gradually into the dense interior below, with nothing to mechanically slow the wind. Once air starts moving, almost nothing stops it. The second factor is shallowness. Neptune's active weather layer appears confined to a relatively thin shell, roughly 600 to a few thousand kilometers deep, wrapped around a planet more than 49,000 kilometers in diameter. Neptune's modest internal heat only needs to accelerate a comparatively small, low-density volume of gas at the very top. Moving a small mass to high speed takes far less energy than moving a large mass slowly. The third factor is temperature, and it works nearly backward from intuition. At about 214 degrees below zero, Neptune's atmospheric gases carry so little thermal energy that their internal viscosity drops dramatically compared to warmer atmospheres. In a warm, dense gas, viscosity acts as a continuous internal brake, quietly converting kinetic energy into heat and slowing motion over time. In Neptune's frigid clouds, that brake barely exists. Once gas picks up speed, almost nothing slows it back down. Put those three factors together and Neptune's atmosphere functions like a flywheel spinning in a near vacuum. Energy enters at the base of that thin wind layer, converts into horizontal motion, and then keeps circling the planet with almost nothing draining it away. It is not a powerful engine running on abundant fuel. It is an efficient one, extracting an outsized result from a very limited supply. Below the visible cloud tops, Neptune's interior stops resembling anything familiar. Under pressures reaching hundreds of gigapascals and temperatures of thousands of degrees, water is thought to enter a state called superionic ice. Oxygen atoms lock into a rigid crystal lattice while hydrogen atoms break free and flow through that structure like a liquid, a substance that is simultaneously solid and liquid, with no analog in ordinary experience. Laboratory experiments using laser-driven shock compression have confirmed that superionic ice genuinely exists at the pressures found inside Neptune. Methane behaves even more strangely. Its molecules may be forced apart entirely under these conditions, with carbon atoms compressed directly into solid diamond crystals while freed hydrogen rises upward. Scientists call this process diamond rain, a continuous precipitation of solid diamond slowly sinking through compressed fluid toward the core. Dense diamonds sinking through lighter surroundings release gravitational potential energy as heat, potentially generating new thermal energy inside Neptune right now, supplementing formation heat and helping explain why its internal engine has remained so much more active than Uranus's after 4.5 billion years of cooling. At the very center sits a rocky core estimated at roughly 1 to 1.5 times Earth's mass, compressed under pressures nearly 7 million times greater than what we experience at sea level, with temperatures approaching 5,000 degrees Celsius, comparable to the surface temperature of the Sun itself. This is not a dormant relic at the bottom of a frozen planet. It is a furnace, radiating heat outward through those exotic compressed layers, driving the convective circulation that eventually reaches the atmosphere and powers the winds Voyager measured moving faster than those of any other world in the solar system. That same exotic interior appears responsible for Neptune's magnetic field, which may be the most geometrically unusual of any planet in the solar system. Earth's magnetic axis sits only about 11 degrees from its rotational axis. Neptune's magnetic field is tilted 47 degrees away from its rotational axis, and beyond that, It is not even centered on the planet. The magnetic center is physically offset from the planetary center by more than half of Neptune's own radius. Rather than being generated near the core as Earth's field is, Neptune's magnetism is thought to originate inside a shell of electrically conductive superionic water in the mantle, a shell-shaped dynamo that naturally produces this tilted, lopsided geometry. This unusual architecture kept one mystery unsolved for 3 decades. Auroras, the luminous displays produced when charged solar particles are channeled along magnetic field lines into the upper atmosphere, had been detected on Jupiter, Saturn, and Uranus through the faint infrared glow of a molecule called the trihydrogen cation. On Neptune, that same signal had been predicted and searched for repeatedly for 30 years. Nothing was ever found. Then in 2023, the James Webb Space Telescope finally detected what 3 decades of searching had failed to catch. Its instruments captured an unmistakable infrared signature of trihydrogen cation in Neptune's upper atmosphere. Not near the poles as on Earth, but at mid-latitude locations, precisely where Neptune's tilted and offset magnetic field would be expected to funnel charged particles inward. The data also contained a second surprise. Neptune's upper atmosphere had cooled dramatically since Voyager's flyby. In 1989, Voyager measured that layer at around 700 degrees Kelvin. By 2023, James Webb measured it at roughly 358, just over half of what it had been 3.5 decades earlier. A cooler ionosphere produces a fainter aurora, one that had apparently been glowing quietly the entire time, simply too dim for any previous instrument to detect. The aurora was not absent. It was invisible to everything that had previously been pointed at the planet. That is a pattern running through the entire history of Neptune science. Every time a more capable instrument turns toward this world, it finds something that had been sitting there all along, hidden only because nobody had previously been equipped to see it. Only one spacecraft has ever visited Neptune. It was there for a matter of hours, more than 35 years ago. Nearly everything described here, the record-breaking winds, the short-lived storms, the internal heat surplus, the bizarre magnetic field, the recently detected auroras, has been assembled from that single brief flyby, combined with observations conducted from billions of kilometers away across the decades since. No orbiter has ever circled Neptune long enough to watch a storm form and die in real time. No probe has ever descended below its cloud tops. Everything about Neptune's interior remains inference and modeling rather than direct measurement. Mission concepts do exist. NASA's Neptune Odyssey proposal and related ice giant mission studies outlined in the most recent Planetary Science Decadal Survey describe what a dedicated orbiter could accomplish. Tracking individual dark spots from formation through destruction rather than comparing scattered snapshots. Mapping wind speeds across all latitudes and altitudes rather than relying on a two-dimensional glimpse frozen in a few hours, and potentially dropping an atmospheric probe beneath the clouds to measure directly what has so far only been inferred. None of it has been funded. Even under an optimistic projection, no mission could realistically reach Neptune before the 2040s. Meaning more than half a century will have elapsed between Voyager's brief encounter and any spacecraft's next arrival. The implications reach far beyond Neptune's own orbit. Thousands of planets have now been confirmed around other stars, and a striking proportion fall into roughly the Neptune size and mass range. Some orbit close to their stars, scorched by radiation. Others drift at extreme distances where starlight barely registers. The old assumption that distance from the host star determines how atmospherically active a world can be predicts that the distant ones should be quiet. Neptune directly contradicts that assumption. A Neptune-sized world orbiting far from its star could still carry a powerful internal engine accumulated during formation. It could be wrapped in a shallow, low-friction atmosphere capable of converting a whisper of interior heat into extreme wind. It could be raging violently in the dark while appearing from a distance as nothing more than a quiet, featureless sphere. The old rule built from studying planets between Mercury and Saturn said that distance from the Sun should determine how alive a world's atmosphere can be. Closer means more energetic, more dramatic. Farther means quieter and stiller. That rule holds impressively across nearly the entire span of the solar system. And then, right at the very outer edge, it simply stops working. Neptune sits farther from the Sun than any other major planet. It is wrapped in some of the coldest conditions ever measured anywhere in the system. It receives so little solar energy that it barely registers on any meaningful scale of atmospheric power, and somehow it moves its atmosphere faster than any world with vastly more sunlight available has ever managed. Its winds would tear apart anything humans have ever constructed. Its storms grow to the size of planets, rage for years, then vanish without warning. Its interior possibly rains solid diamonds toward a core as hot as the surface of the Sun itself. The calm blue face Neptune presents from a distance, the exact color of a deep, peaceful ocean seen from high above, hides one of the most restless and violent atmospheric environments ever documented anywhere in the solar system. It is a quiet reminder that distance from a source of heat does not guarantee stillness, that some of the most energetic places in the universe may also be its coldest and darkest, and that the planet which appears most tranquil from across the solar system may turn out to be the most turbulent world we have ever had the instruments to measure.